Hello. Yeah, so I'm Bjorn Gustavsson. Today I'm going to talk about the history of Beam, especially the parts that I have been personally involved with. We will begin a little bit early, around 1980, when I learned to program on a program calculator, TR-59 from Texas Instruments. It had about 1 kilobyte of memory, so I learned to write small and efficient programs. And there was a users group for the 59 and the Texas Instrument program calculators, and there was a newsletter. So I wrote a lot of articles in that newsletter. A little bit later, I moved on to the Texas Instruments home computer. It had a very slow BASIC, but I mostly programmed it in Forth and assembly language. And there was a newsletter for that as well. This will actually become relevant a little bit later. But now, enough about me for a while. In 1986, at the Computer Science Laboratory, a project was started to figure out how to best program telephone exchanges. It was not the intention to create a new programming language, but that was, of course, exactly what happened. A prototype for Erlang was developed in Prolog, but it was too slow for real applications. So a little bit later, in 1999, an abstract machine was created, JUICE Abstract Machine, or JAM, and there was a compiler was implemented in Erlang, and the runtime system was implemented in C by Mike Williams, and the compiler, I suppose, it was Joe and Robert that created the compiler, I suppose. And JAM was a stack machine. So to calculation stack machine, you first push values to the stack, and if you auto evaluate 37 plus 5, first we push 37 to the stack, and then 5. Another plus operation will add them, and pop the numbers, add them, push sum back to the stack. It's very easy to implement a stack machine. And JAM turned out to be about 70 times faster than Prolog implementation. But people still wanted more speed for real applications. So Bogomil Hausman invented what he called Turbo Erlang. And it was said, it compiled Erlang code to C code. And it was said to be about 10 times faster than JAM. So here is an example of, here is an Erlang function, the append function, and here is how it looks compiled to Turbo Erlang. This is from an article that they wrote at that time, the Bogdan wrote at that time. And so each instruction is a C preprocessor macro, which is then expanded to a lot of C code. So that is how we looked at that time. But the code turned out to be very huge code generated by this, but first compiling to C and then compiling to native code. So it turned out to be not practical for real applications, because so that memory was used only by the code. And compilation was very slow. And also the name didn't fly. But Bogdan didn't give up. In 1994, he created Bogdan's Erlang Abstract Machine, or Beam. And here there was a choice to compile either to C code or to code for an abstract machine, for the Beam machine. So the idea was that one could make a trade-off between speed or memory usage. So to get the most speed, one could still compile to C code. But for modules that didn't need that speed, they could be compiled to Beam code for the for the virtual machine. And Beam is a stack machine. Redis machine. A Redis machine is more complicated to implement, but one can usually get better performance by using a Redis machine. So here to evaluate 37 plus 5, first we need to move 37 to an X register, to X register 0. And then we'll have to move 5 to another register, to X register 1. And then this plus operation will add these numbers and put them into the X register 0. And I just want to say that I made many simplifications to make this clearer in previous slides and in coming slides, just so that you know. In 1996, the Open Telecom platform was invented, and there was a group formed, the OTP team. They had offices in the same building as the computer science laboratory. That was in Älvsjö, Götalandsvägen. At that time, I worked at the Ericsson, but not with Erlang. But I happened to work in the same building. So one day when I was going home on the bus, I happened to meet Tony Rågvall, which I happened to know from the newsletter. He had written some articles about assembly language programming on the home computer. And now he worked at the CS lab, and he persuaded me that I should also start working, developing Erlang. And so I did. I started working at OTP at the end of 1996, and the next year I started to work with the Beam. Before I go on, I want to talk about the meaning of Beam today. Usually it's meant the entire runtime system, including scheduled garbage collection, all built-in function drivers, and so on. At that time, Beam meant just the code loader and the thread interpreter. And yeah, that was a part that I had become responsible, the main responsible, very soon after I started working at the OTP team. And then I've been the main responsible for many years. But just for this small part, there are other people in the runtime team that have developed the other great features of Erlang. So at that time, we had to maintain both Jam and Beam, and the long-term goal was to make Beam good enough so that we could retire Jam. There was some challenges to doing that. We needed to get Beam good enough so that we could maintain it. It must be maintainable. So the first problem was the loader. Beam had more than 300 instructions at that time, and each instruction needed a handwritten code in the loader. I will show you soon what the loader does. And then the Beam file format was not stable from each release. They had a version number in the header of each Beam file, and it was updated in every release. And that means that all users had to recompile all the Erlang code every time we release something. This also had to be fixed. Okay, so now we'll take a closer look at Beam. And so I already shown the X registers that use the temporal values and for passing arguments to functions. And they're also on the stack. The stack slots are called Y registers. So here are 3 different stack frames. The continuation pointer is also called return address. It's return address of the caller, the function to call this one. So let's look at some move instructions. Move x2 to x1. And now we'll move x3 to y raised to 0, like so. And finally, we move the atom arrow into x2. So the move instruction didn't look like this actually in the old beam. It looked like this. There were multiple move instructions depending on the type of the operands. So first we have moving x to x, x registers, or move xy, moving from x register to y register, and so on for the other variants. And they were assembled to beam bytecode like this. First the number on the instruction, then two bytes for each operand. But when loaded, this would be expanded. So each move instruction would be expanded to 3 words or 12 bytes. And the reason for that was the way beam worked. The first word in each instruction contained a pointer to executable code. And that means that the other operands, they need to be aligned on word boundaries. And this thing, this double ampersand, is an extension to C in GCC. It's called labels as values. You can take an address of label and then later make an indirect jump to that label. So when I started out working, I decided I must do something about the handwritten code in the loader. So I decided to write a Perl script to help me. It's called beam makeups. And it would take some input files and from that generate some output files mainly for the loader, but also for the compiler. So let's look at the input files. So we have the genop tab file, which gives the number of the instructions or opcodes for all instructions. And also decided that the compiler shouldn't need to know about the different move instructions in the runtime system. One move instruction should be enough. So I changed it like this, one move instruction and having the types in the operands for each instruction. And I changed how the encoding operands to make it smaller. There were some complaints that beam files were very large compared to gem files, so I wanted to address that as well. And then we have another file for the beam load runtime system. Here we list all versions of move instructions. Move x for moving x register, and so on. Move x means moving a constant to x register. A constant is an atom or integer. And then for implementation instructions, here's a template for a move instruction for all of these move instructions. And the script would expand that to the actual implementation. And I will show you the complete implementation a little bit later. So here's the implementation of the move xy instruction, moving from an x register to a y register. When loaded, it would look exactly as before, except that the compiler was simpler and all that huge handwritten code was removed. The script made all that work. But now having a script that generated code, I could do more optimizations. So 3 words for move instruction is a little bit wasteful. It's wasteful to have a complete word for a register number. 2 bytes would be enough. So I changed the beam makeup script so that it could pack the operands. and unpack it at execution time. So from this same template, this is the complete code that will unpack over operands. You're using shift instruction and bit masking instructions. There was an optimization in the old Beam compiler to combine certain sequences of instructions. A very common instruction sequence is a move followed by a call. And the compiler would combine them to a move call X instruction. My new compiler didn't do that. I wanted to keep the compiler simple. Instead, I invented something called transformation rules in the loader. So in the loader could match instructions and then replace them with something else. Let's look at an example how this is done. So here in the middle box are 2 instructions, and in the top box is the transformation rule. So here we see that the first pattern will match. The first operand is a constant or a register, and the actual instruction is an integer, which is a constant. So that matches, and the X register should be 0, and it is. So that matches. Now the second instruction will match a call X, and it is a call EXT instruction. So that will match, and now these 2 instructions will be replaced by move call X instruction in the loader. So no need to update the compiler to add additional optimizations. And having this mechanism in place, I could introduce other optimizations that were never done in the old Beam. For example, 2 move instructions could be combined into 1 using this rule, and resulting in smaller and faster code. So the other challenge I mentioned was the unstable Beam file format. The main reason for that was calls to built-in functions. So make ref is a built-in function, and it needs to be called in a different way compared to calling an ordinary Erlang function. So it used this BIF instruction and had an index into the BIF table for the runtime system. And the compiler and runtime system needed to agree on how BIFs were numbered. So that's why we had to have that version number in the Beam header. So to fix that, I changed the calling convention of BIFs so that it became the same as for ordinary function calls. And I added a small optimization to translate that in the loader. So if a call happens to be to a BIF, like in this example, call to make ref, it will be replaced with a call BIF instruction, which is a little bit cheaper to execute. So this is a summary of the first part from my talk. So I introduced the Beam makeup script problem in UTP R3, and it helped me to optimize Beam to make it faster. So the support for generating C code from Erlang code, I could remove that because it was basically no longer needed. The Beam was about as fast as C code, and it used much less memory. And UTP R5 changed the format of Beam file, introduced a new file format, which is used to this day. This new file was more extensive than the old one. And in UTP R6, we could finally retire jam. Some users still wanted more speed. So it seemed I couldn't do that much more with the Beam runtime, the Beam and runtime system. So started focus on the compiler. So now we'll talk a little about the Erlang compiler. Compiler user have multiple passes, and so here is Erlang compiler to high level view. There's a front end and a back end. One back end for Jam and one for Beam. So let's now first look at the front end. So it's the front end for that was shared between Jam and Beam. And we'll actually show this is examples. I will about these three passes. So say if you have this original Erlang code, when it's parsed and transformed into abstract format, records and exact weight space will be lost. So after parsing, we have the same program, but represented in a different way internally. And here's just pretty printing out to show that the comments have been removed. And if you are on Erlang program, you know that there is a preprocessor in Erlang, similar to the C preprocessor. So after that has been run, now that macro has been replaced with actual value 42. Records are just tuples under the hood. So when the preprocessor for records will run, it has been replaced with tuples, the record on the last line. So now let's look at the backend. The backend takes the preprocessed Erlang code and translates it to code for the Beam machine. So the first original compiler had the first pass translated it to Beam instruction. Then was an optimization pass on this instruction. Then they were assembled into Beam files. And we wanted to have a compiler that did more optimization. The Beam compiler did better, produced much better code than Jam. Then we still wanted more speed, more optimizations. For example, of pattern matching compilation. So in this example, we have a case with 3 clauses. And first we look at how that was compiled for Jam. So Jam would match each pattern in function clauses or case clauses in sequence, just as if you have rewritten the Erlang program in this way. Beam did a little bit better on simple patterns. I think it would optimize this a little bit better. It will first match the tuple, and then match the first element of the tuple. But Beam, for more complicated patterns or for deeply nested patterns, it would still do unnecessary work, repeating matches and so on. And so for this example, we wanted code like this. So we wanted first to order all tuple matching together and all eto matching together and do them in order like this. So we want a better pattern match compiler. And we will look, where could we find a compiler? Well, we happened, Robert Warding likes to implement programming languages, and he also had his own implementation of Erlang. So he had his own working Erlang engine, or V, and the original V was a stack machine. We don't know much more about it because it's never been officially published as far as now. But Robert planned to make a new V that was a register machine or to add additional optimizations. So I think it probably looks something like this. Pretty similar to Beam, but not exactly Beam. But that didn't actually exist. Robert had implemented yet, but he has written a compiler for it. So here are the main passes for his compiler. This first translation to something called kernel Erlang. It was intermediate format based on Erlang, but different. I will not show you that. And then pattern matching compilation, and then generate of the instructions in the last pass. And actually, by rewriting this pass, it was possible to make this a Beam compiler. So I did that. I rewrote that last pass to adapt it for Beam. So in OTP R6, we ended up with the following main passes. This was the default compiler in R6, and there were also options to select the old one or the new one that was experimental. Okay, so now I will move on to what we did for R7. And for R7, Rickard Karlsson and the Hype team at Uppsala University suggested a new intermediate representation for Erlang programs called Core Erlang. It was simplified and restricted version of Erlang, but it would be easier to do optimization on it, and it could be a common intermediate representation for doing research on compilers and other tools such as inliners and so on, everything you can think about when researching compilers. So here I'll show you a simple example. We have this Erlang code, and this is preprocessed Erlang code. Also, the call Erlang, all atoms are quoted to make it simpler, and all clauses need to have guards, even if they are true. So it's simple and more restricted, and it is easier to optimize. So here we have this binding of variables that can be optimized simply like this. And now we have on a clause. This clause will always match because there are no patterns in it, and the guard is true. So all clauses after it can be removed. And now we have a case with the single clause, so we can eliminate the case. So it's pretty easy to do such optimizations in Core Erlang. So in OTP R7, we ended up with main compiler passes. So the translation to Core Erlang, written by Robert, and then optimization pass for Core Erlang optimization, and then the kernel Erlang was still used because they had pattern matching compilation inside, and then the code generator to Beam code. And then I added some optimizations passes on Beam code. This one was added in OTP R7. There were to be more, spoilers, but there were to be more than these passes in later versions. Yeah, so now we will look forward to OTP R12 on looking at the important optimization added at that time called stack trimming. So we have, as an example, show how this Erlang function is executed. It's a map function. Will be called in this way with a list of 1, 2, 3, and it will return a list of -1, -2, -3. The main point of all this, if you don't follow every little detail, it's the number of stack slots that are used in each iteration. So first here, when entering the map function, the arguments are in X registers. So you can see in X is 0 and 1. And first will happen in the function, a stack frame will be allocated, and things that will be overwritten X registers will be copied to Y registers. And next, after done pattern matching on the list, now we have the head of the list in X register 0, and then we save the rest of the list in Y register 1. So now we can call the fun, getting back -1, and that need to be saved on stack, and then we'll move back the fun to the X register 0. So now we are prepared to call map recursively with a smaller, shorter list than before. And after this iteration, it will look like this, an even shorter list. And now we reach the end of the list. So now we can start returning. We'll return, and then we'll build the list in reverse. So we will take the -3 from stack, put that into the list. Now we'll take -2, and so on. So here they have the result. The problem with this is that temporarily needed to save the rest of the list to the stack, but is then never used again. And this, if there were to be garbage collection, the garbage collection would have to copy it, and that was totally unnecessary. So in R12, I had a new stack trimming pass called beam trim to the other optimizations pass operate on beam code. Now we look how to evaluate this with stack trimming. So we start in the same way, execute in the same way. But here, before doing the recursive call, we will do stack trimming. And now we will drop down to the beam level. So first, we want to save the -1 in another Y register, like so. And now trim, it will remove one element from the stack, like so. And then we can do the recursive call. And then we can repeat that. So we only save the things on the stack that we actually need. Okay, and then we unbind the stack as usual, building the result in the same way as before, but using less stack, so it's more efficient. Okay, so now let's jump ahead to binary matching. There is an optimization of binary matching. So basically here it doesn't really have to build this binary for real. It tells what is called match context match, and we can keep the match context. So this is an optimization so was introduced earlier. And so this optimization would be applied in UTP 2021 for this code. But if you did a simple change to this code, for example, say we want to move this yellow expression in yellow to a helper function, perhaps to match more white space, this optimization would no longer be applied. So we wanted to fix that. So in around UTP 21, John Högberg joined the compiler team, doubling the number of people in the compiler team. And he worked on improving this BSM pass to apply this optimization more generally. And he succeeded. Unfortunately, working on the Beam code that was never meant to be optimized, heavily optimized. this was tricky. So there was a lot of code was needing to achieve that. So we decided we couldn't really use this code. It would be too tricky to maintain and keep it right, and also be sure that it really was right. There were a lot of code special cases. So we understood we have reached the end of the road. We couldn't really continue to adding optimization parts of optimizing Beam code. So we wanted something better, to optimize before generating Beam code. So we introduced static single assignment, or SSA, which is used in other compilers. We wrote our own implementation. We don't use Erlang VM or something else. Everything is written in Erlang for these optimization processes. So we will look at this function and see how it's translated to SSA. So it looks like this is 3 blocks, and I will show you, visualize that in a different way. It could be a little bit easier to understand. So comes in here, do a plus operation, get the result, then we test, did it succeed? In that case, we can return it. Otherwise, we'll jump to here, and this will generate an exception. So this is much easier to optimize, and then optimize in Beam code. So in OTP 22, we added translation from core Erlang to SSA after the core Erlang process, and then we added number of optimization processes, which I will show. And we could take out optimization. So we didn't need all the core Erlang optimization because they could be done better in SSA. And also we could remove a lot of optimization processes operating on Beam code. So here is a comparison of the optimization process operating on Beam code. OTP 21 in the left column was all the optimization process, and in OTP 22 the one that we still needed to keep. That was thing that could be done before allocating X register and Y register, so on. So it needed to be done later. I might have forgotten the Beam trim pass. I think should still be there. Seems that I've forgotten to add that. So there were a number of SSA passes optimizing SSA code written by me and by Bjorn. So Bjorn wrote a better version of his optimization pass optimized to SSA, which was much easier to understand, and also applied optimization in more places. And I will show you one particular optimization. So type analysis, determine types. So I wrote a simple version of that could do it within a function. So when we come into a function, all the types of variables are unknown. But when we do certain operations, we can know that if the operations succeed, the variables must have certain types. So if this plus operation succeeds, we know that all of A, B, and C must be numbers, integers or floats. But there must be numbers. Otherwise, this will raise an exception. And if you do the rem operation, the remainder operation, that only accepts integers. So now we know if it succeeds, we know that C and D must be integers. And similarly here, if D plus 1 succeed, E must also be an integer. John extended this to work within a complete module. So when entering an exported function, all arguments are unknown. We can't know the types. So if I have this a function which is exported, and this calls to length. Length will succeed if L is a list, and when that succeeds, we know that L is a list, and we know that the return value is an integer, is 0 or greater. So we know that common in this case will be called with an integer. And B, which is exported, I plus 1 must be number if it succeeds. We know that in this case, comma will be called with a number, a float or integer. So when entering common, which is not exported, we know that n must be a number. Unfortunately, it could figure out a lot of types, but it couldn't do that much optimization that we would have hoped. In UTP-22, but we'll come back to that. So in UTP-24, the just-in-time compiler JIT was introduced. There have been 3 previous projects trying to build a JIT in the traditional way to figure out where is the hot code and then do compilation that to native could do the good compilation that native could. But turned out it didn't really improve the performance of real applications. They could do it for some benchmark. But after I've just finished the third of these projects, Lucas Backström, or Lucas Larsson, as known at that time, and John Högberg, I wanted to try do a new attempt. The idea here was to not try to figure out the hotspots, but to translate all Beam instructions to native code in a simple way. The native code would not be as good, as highly optimized as another JIT approach, but all instructions would be translated, and maybe that would work better. Well, spoilers, it worked better, as you all know. So here for these 2 move instructions, the loader will translate them to native instruction on an x86. See in 16 bytes, 4 instructions, 16 bytes will do that. And the loader could still be used to do optimizations for the JIT. So for example, there could be a rule to translate certain move instructions into single instruction. For example, these 2 move instructions would be translated to move towards instruction. And the JIT could generate smaller and faster code for this, only 12 bytes. So it would read 2 words at once from memory into a SIMD register, and then swap them, write them back into memory at once. Okay, so now take a look at the plus operator in the JIT. So look like this in Erlang code. And here is the Beam assembly code. And translated to native code, there are quite a lot of instructions, and one might ask why do we need that much code to add 2 integers? Well, that should really need that much code. But actually, okay, we're not only adding integers. We could be adding integer, of course. We could also add a floating point number, or large integers that don't fit into one word. They are stored in the heap. Or we could pass in something that is not a number, and it needs to raise an exception. So that's why a lot of code needed to handle all those cases. So in UTP-26, we added a new optimization to keep track on ranges for integers in the compiler. And the compiler would output into the Beam file a type for when it could figure out the type. it would put that into the Beam instruction to include in the Beam file. So here it says that this x0 must be an integer in this range 0 to 1023. So when the loader sees this information, a lot of those instructions are no longer needed. And some further simplification, we end up with 3 instructions, which is much nicer. Okay, so yeah, I seem to reach the end of this talk. Personally, seems I've come full circle, starting writing articles about TF559, how it works internally. I was digging deep into that and writing articles about it and how to program it. And now lately, I've written blog post about how the compiler and the JIT and the Beam works. Well, if you want to know more, there is the Erlang blog, and with blog posts by me and my colleagues in the OTP team. If you're interested in the Beam makeup script, it's actually documented in the internal documentation for its application. I think that's all. Thank you.
Thank you very much, Bjorn.
Okay.